Alrighty, everybody. So I've posted just above this on the page links to the Veritaserum videos that go over the same exact introductory stuff that we did in our activity with the ice today. So if you want a little bit of a reboot on that or another take, go ahead and check those out. So I'm just going to start here where we actually started digging in. So remember, we're talking about thermochemistry. This is for our ALT 7, right? Thermochem. So we talked about how there's kind of two sides to thermochemistry. There's the physical side and the chemical side. Also, remember, we already have done most of the physical side. We just haven't done the math for it. So the ideas around it, we should already be relatively familiar with, at least most of them. And then later on, in a few days, we'll hit the chemical side where we'll start looking at the energetics of chemical reactions and chemical potential energy and that kind of stuff, the energy parts of chemical reactions. So for now, we're going to stick with the physical side. So here's a list of the vocabulary we used. I'm going to give you an example to kind of set you up for thinking about our lab, and I will use every single vocabulary word in context when I do that. I promise. It is my challenge to myself, so we'll add that at the end. So make sure you've got an understanding of what each of these words are. So then we got specifically into heat capacity, more importantly, specific heat capacity. Basically, from this point forward, if we refer to heat capacity or specific heat capacity, but same thing, think specific heat capacity. That's what really matters to us, right? Is that intrinsic property of a substance, the amount of energy it takes to raise the temperature of 1 gram by 1 degree Celsius. So we played around looking at the units of C, right? This symbol we're using for specific heat capacity. Remember, we're using Q for heat, M is mass, T is temperature. Anytime it's a delta, it's a change. So just kind of diagramming out this fundamental equation that we're going to be using in thermochemistry. Q equals MC delta T, Q equals MCAT. You might have heard it referred to. So again, the math moving forward with this is all algebra. So, if it makes you feel better every once in a while, just swap out all of these variables that have meaning and throw in your X's and Y's if you really, really want to, just to remind yourself, oh, wait, it is just algebra. I understand it's harder in context, but I promise the basic skills are identical. All right, so then we did a quick problem, right? I gave you all the variables up top, and we realized, so if we're looking for the initial temperature, we could plug T final minus T initial into that area for delta T in the Q equation. However, I find it easier to just go ahead and solve for delta T and then solve for the temperature that we are missing. Is it as elegant? Maybe not. Maybe I just don't trust my algebra skills that well. I just don't like doing it all together. So again, for me, I like to rearrange my formula before I use it. So we take the Q equals MC delta T equation and rearrange it to solve for delta T. So that gives us delta T is going to equal Q over MC, right? The heat that has been transferred over the mass of the substance times its specific heat capacity. Really important that those variables that we are using are matching the substance we're talking about. So the mass matches the thing that you're using the specific heat capacity of, which matches the temperature change happened to that substance, right? And the Q, the heat exchange, happened to that substance. It all has to relate to the same thing. So for this example, plug in the numbers, double check that the units all work out. They do, right? I talked about how you can use dimensional analysis in algebra problems as well. When you have big formulas, even small formulas with different units that have different constants that have different units and so forth, you can always double check those units to make sure you're plugging everything in correctly. So again, we just did some algebra magic and came up with an answer. What I came up with in class was crappy significant digits, so I switched us. We should have had about 1200 degrees C negative, okay? All right, so now let's move forward onto new territory. So here was an example that I wanted you to do in class, and actually I'm not gonna do this one because I want you to do this one on your own. It's basically just like the example that we did just now. It's just easier. You're solving for Q, right? So Q equals MC delta T. I'll just diagram it out for you because I can't help myself, right? So Q equals MC delta T is the equation we're going for. Up here, right, that 0.9 joules, that is our C value, right? 851 grams, there's our M, and there we go, we have our delta T. Our T initial is the 22.8, and the T final is the 94.6. We know this because it says it's going from 22.8 to 94.6. So there you have all your variables, solve for Q, you're good to go. All right, so next, this is the thing I didn't get a chance to show you, and I want to. It'll make it so that you can actually start working those more challenging problems. So to do this, let's do my scenario, and this is where we're going to use all of those vocabulary words, and I'm going to kind of introduce the lab here. So in the lab, we're going to use that technique called calorimetry that I kind of introduced, right, using that insulated cup and so forth. So we've already kind of talked about this idea. So let's just get a picture of what's going to happen here. We're going to have our insulated cup, right? In it, we're going to have some water. Okay, and then let's say, oh no, that's a weird example. Okay, so in it we'll have some water, and then into the water we're gonna place a block of metal. Okay, so the block of metal is gonna be hot, and the water is gonna be cold. Okay, so what's gonna happen here? So let's figure this out. In this example, I want to go through all of my terms. So first of all, since I'm doing a thermochemistry experiment, I'm going to want to define my what I've got going on. So I'm going to define my water as the surroundings, right? And my metal chunk as my system. Okay. I'm going to say that I know that since this is hot, it is going to transfer heat from itself, which is the system, into the surroundings, which is the water. So the heat is going to transfer into the water until they reach thermal equilibrium, where their temperatures will be equal. So I would consider this to be an exothermic process in relation to our system, which is the metal cube. If we reversed and started calling the water our system, then I would consider it endothermic, because the water is going into, or the heat is going into the water. Now, depending upon the heat capacity of that metal, that's going to determine how much heat is released, right? The mass of the metal is given. The heat transfer that we get from that is then going to depend upon that heat capacity, which will then also influence that change in temperature. So if we use a block of copper versus a block of aluminum, they will have different heat capacities. Therefore, that amount of heat that is released is going to change. And then also that final temperature is going to change, right? How much heat that substance can hold on to at a certain temperature is going to be different for different substances, okay? So that's where that specific heat capacity comes in. So now let's look at what math we could do here. And this brings us into our next idea. So let's consider the metal, okay? So let's start with looking at the metal. If I wanted to figure out Q for the metal, okay, I'm going to say, all right, so for the metal, I'm going to have Q equals mc delta T, right? So Q is the heat leaving the metal, right? Heat leaving the metal, okay? So, great. Let's look at the water for a second. Let's say we wanted to do this same exact thing for the water. Okay, I could come up with my Q equals mc delta T. Now, that Q, what is the relationship between the Q of the water and the Q of the metal, right? The Q of the water, it's always the heat being transferred, right? How much heat moves. Well, what heat is going into the water? It's the same exact heat that is leaving the metal. So this is the heat entering the water, right? So my argument, and I promise I'm right, is the fact that, Q for the metal is going to equal Q of the water, okay? They will be the same value. However, they're going in opposite directions. And so in thermochemistry, we consider a negative value to be exothermic and a positive value to be endothermic. So a negative heat value means heat is leaving. A positive heat value means heat is coming in, okay? Heat is being added. A positive means added. A negative means being taken away or leaving, right? So I'm going to go ahead and pop my negative sign in front of the metal. Honestly, it could go on either side. It doesn't matter because the value you get will be correct, but they are opposites. That's the whole point. The Q, or the heat leaving the metal, is the opposite value of the Q entering the water, right? Because we assume, and this is the critical part, we are assuming 100% heat transfer, right? We're assuming that no heat is lost anywhere. And I think you can imagine that that's probably a bit of a false assumption, but we have to assume that. Otherwise, these problems get much more complicated and harder, okay? So these are the ideas here. Q of the metal is going to equal Q of the water. So now, check out what we can do. So let's say I'm doing a problem here, and I don't know what that Q is, and I want to find the identity of my metal. That's what you're going to be doing in your lab. So you're going to want to find C, the specific heat capacity of that metal, right? Right here. This is our unknown, is C. We can calculate the mass. That's not a problem. Or not calculate, we can just measure it, right? Delta T, temperature. Well, we can take the temperature before and after, so we could figure out our delta T. We don't have our Q, okay? But what about on the water side? On the water side, we could weigh it. We could know the mass. The C value, I'm going to give you. It's 4.18. I'm not worried about that. So you know C for the water. And again, you could measure the change in temperature of the water. So notice we're missing Q for both, but then we're also missing C for the metal. But if I take this equation, right, and use it, but substitute my MC delta T for my Q values, all of a sudden I've created an equation that eliminates the need for those Q values. So it's okay that I don't know them because I know that these two things are going to be equal to each other. So I could do this again, and I could say, all right, well, this is just the same as saying negative mass of the metal, C of the metal, delta T of the metal, right? So these are all for the metal, is going to equal the mass of the water, the C of the water, and the delta T of the water, right? That side's all for the water. By doing this, now let's double check our variables, right? We can measure the mass of the metal, we can measure the change in temperature, we can measure the mass of the water, we know C for the water, and we can measure the change in temperature of the water, leaving us with one single variable to get. Okay, so this is what we're moving into, and this calorimetry experiment is what we're going to be doing next class. And so I want you to be able to do the math for it. So that's what this is about. So now here is an example, I think. Yeah, here's an example, kind of simpler, I guess. I don't know why I had you do number 3. Maybe this is a little more awkward. Let's go ahead and actually, let's skip this. I know I told you to do 3 first. Let's do number 2. So number 2 is exactly like what we're doing in our lab. Okay, so let's do some diagramming. I'm going to use red for my metal and blue for my water. So here is my grams of nickel, right? So there is my mass of the metal, okay? It is heated to 98 degrees C. So this is my initial temperature because the calorimetry hasn't started yet. The heat transfer hasn't started yet. So we just made it hot. So this is my initial temperature of the metal. And the final temperature of the water is 25 degrees C. So that is my T final of the metal as well, right? Thermal equilibrium tells us that they are going to both be at the same temperature in the end. All right, so I've got all the variables there. I don't have the specific heat capacity, but that's what I'm supposed to calculate, right? So my question is specific heat capacity of the nickel. So I am looking for C of the metal. That is my main question, all right? So let's see what else the problem gives us. It also tells us that we have 150 milliliters of water, okay? So this we can turn into the mass of our water, right? We can use density of water to get mass there. We also know the initial temperature of the water right here, right? And remember, these are going to be the same, so this is also T final for the water. Okay, so again, this is just like what we looked at in the previous page. We have everything except one of the variables as long as we don't have to think about those Q values. And we don't. Anytime we're doing a heat transfer, we can make this assumption that the Q of the metal is going to be opposite the Q of the water. Okay, we get to make that assumption. And we know that Q equals MC delta T. So let's create our equation, right? So Q of the metal, so it's going to be negative, and let's go ahead and use red for these. So the mass of the metal is the 22.8 grams, right? There's our mass, times the specific heat capacity, which we don't know, that's our variable, times our change in temperature, which is T final minus T initial. So our T final is 25 degrees, and our T initial for the metal is 99.8 degrees. Okay, so there we go. Now we have our left side of our equation. This is our metal side, right? This is all for the metal. All the information on this side is all about the metal, okay? This is going to equal Q for the water, okay? So let's start that. Q for the water, let's see, the mass is 150 milliliters, and we know that the density of water is H2O, right, is 1 gram per milliliter. So if we have 150 milliliters, that means we have 150 grams. So I've got my 150 grams of water times my specific heat capacity, which is, let me make sure my brain is not turned off. Yep, 4.18. So times 4.18 joules per gram degrees Celsius times the change in temperature, again, which is our T final minus T initial. They had the same T final, so there's our 25 degrees C minus the initial temperature of the water, which was 23.5 degrees C. And I'm just gonna shrink us, not that much, shrink us down a smidge so that I have room here. 23, that's a 0.5, sorry about that. There we go, there's our T final, and there's the right-hand side of our equation, okay? And again, this is all about the water. So we know Q of the metal is opposite in sign of Q of the water. That opposite in sign part is why we use that negative sign. And let's see here, we end up with, let me see if I can cheat and steal Miss Miller's work here. Yeah, let's just, no, that's not what I want. T final. This isn't solving for T. Oh, I'm looking at 2. All right, there we go. I was crazy for a second. All right, so we end up with C times, all right, 1705.44. Okay, and that is going to equal 140.5. Now, shame on Miss Miller for not including her units. I argue that the units on the right are going to probably equal joules, right? I think they do. They do? Good. And the units on the left are going to be bizarre. It's going to be grams times degrees Celsius, okay? So let's get grams degrees Celsius, but those are on the top, right? Those are not a fractional thing. So if we want to get C, then let's do some work, right? C is going to equal 940.5 joules divided by 1,705.44 grams degrees Celsius. Look at that. Now we have a number that we're going to get with units of joules per gram degrees Celsius, which is exactly the kind of units that a specific heat capacity value should have. What do we get here? We get 0.5514 blah, blah, blah joules per gram degrees Celsius. Let's get some sig figs on there. And I think we get 3. Am I right about that? Yep, we get 3. So we'll call this 0.551 joules per gram degrees Celsius, right? This is the C of whatever metal we're dealing with, nickel. Oops, that's an N-I-C-K-L-E, whatever, okay? So there you go. So this is kind of the complexity level of these questions that we're gonna have to do, and we're just setting 2 equivalent equations equal to each other. That's reasonable algebraic thinking, okay? So this is the last one I wanted to show you. Please follow my example. I know it's a little bit of a pain, but include those units, all right? Good luck. I had a fun time in class today. I hope you guys did too, and I will see you next time. I put another one on there for you. Oh, there's the key. So if you're going through, take a peek at that. This is Miss Miller's work. She does her work slightly differently than I do, but I'm lazy and I didn't want to use a calculator, so I just kind of stole her key. If there's any problem with the math, we can blame her. And I encourage you to not follow her example here and use your stinking units. I'm going to have to get on her case about that. She knows what those final units should be. You guys don't, right? You need to be working that out.